Welcome all viewers again in this paper operating system, and the topic is scheduling algorithm. And in scheduling algorithm we first discuss the first come first serve scheduling algorithm. So we have discussed in the previous class there are the two type of scheduling philosophies are there. Preemptive scheduling and non-preemptive scheduling are there. Preemptive scheduling is that scheduling in which the processor may, any process may ask for the CPU in between the processes running. While in the non-preemptive scheduling, until and unless the process has finished its work, the process cannot ask for the CPU. So these are the two types of, scheduling philosophies are there. On the basis of that, we are, discussing now different type of scheduling algorithms. So first is the first come, first served scheduling algorithm. And after this reading, this lesson, you will be able to understand the concept of first come, first served scheduling. What is it? And how it's working, in the operating system, and what are the various advantages and disadvantages of this, scheduling algorithm. So let's move on. First come, first serve scheduling algo is what? There is always a simple approach to maintain a queue, and that is the item that comes first will be served first. And it is in tune with this, natural justice that people waiting in a queue will be served first. It is in tune with this natural justice that people waiting in a queue will be served according to their position. Like the person which comes first in the queue comes first, that is the simple queue process. So the person in first position will be served first, and the person in the last position will serve last. So the ready queue can also be, maintained with this approach as soon as the processes are arrived in the ready queue, and the arriving process is added onto the tail of the queue, and at the end of the process, at the head of the queue is dispatched to the processor for execution. So in this way, a ready queue, is implemented as a linked list wherein order, like first in first out queue. If you remember that, process state figure, if the process is there and they are in the, if they are in the ready queue, say for example, this is the ready queue, and processes are, placed in this position. Say for example, this is process 1, this is process 2, and this is process 3, and this is process 4. So that process 4 comes at the end of the queue. Therefore that is the meaning of tail of the ready queue it is put. And this is first process which comes first, it is put in this head of the queue. So that is the meaning of tail of the queue. If you remember this, we already discussed in the ready queue in the process states figure. So like in first out, these processes are put in the ready queue. So a running process, if interrupted, is moved back to the ready queue and added onto the tail of the queue. It means a process that has been interrupted by any means, so doesn't maintain its previous order. ऐसा नहीं है, like I gave you the example in the previous class as well, कि आप लाइन में फॉर्म के लिए खड़े हुए हैं एंड आपने सपोज करिए किसी भी वजह से इंटरप्ट आता है, लाइक आपने फॉर्म में फोटो पेस्ट नहीं किया और आपके पास फोटो नहीं है, एंड यू गो बैक होम, यू back with this photo and you paste it on that form, and आप कहें नहीं मेरा नंबर तो पहले था, मैं तो यहाँ से सीट छोड़ के गई थी तो आप लगाइए. It doesn't like this. So if interrupt occurs in between, so it doesn't mean it guarantees that same order maintained like in the previous ready queue. So once it has been dispatched to the processor, it has no arrival order. If it comes back in the queue, it acquires the last position. So this scheduling policy is non-preemptive, because the process which arrives first will be executed first, so to its completion. So obviously this scheduling policy is useful in batch system where the jobs of users are ordered and executed as their arrival time, according to their arrival time. So this is the order of this or you can say working of this scheduling technique is there of the FCFS policy. And we, as I discussed with you in the last class, previous classes as well, that that scheduling algorithm, why is it necessary to maximize the CPU utilization, to reduce the waiting time, and there are some criteria through which we are needed this scheduling algorithms. So that CPU scheduling also deals with the problem of deciding which of the processes in the ready queue is to be allocated of the CPU. So that is also the important point for this purpose of scheduling algorithms. So as I told you, as far as this concern of the CPU scheduling and this FCFS, it is the simplest form. So with this scheme, the process that requires the CPU first is allocated the CPU first, and the implementation or FCFS policies are easily managed by this FIFO queue. So we take this example and try to understand how this happens. So when a process enters the ready queue, its PCB, that process control block, is linked onto the tail of the queue, and when the CPU is become free, it is allocated to the process at the head of the queue, and then the running process is then removed from the queue, and the code for FCFS scheduling is simple to write and understand, and each and every entry is entered in the process control block. So let's say, for example, what is the average waiting time for FCFS scheduling, and then on the basis of that we can decide whether it is good scheduling policy or not. So let's say, for example, there are the three processes are there: process P1, process P2, process P3, and this is the burst time of this processes are there. P1 CPU burst time is 24. All the times are in milliseconds. And P2 is in your burst time requires 3 milliseconds, and P3 is again 3 milliseconds. And we imagine that the processes arrives in the order like P1, P2, P3. Like first P1 comes, then P2 comes, and then P3 comes. It means that at time 0, that P1 process arrives, right? So if we follow the FCFS order, so how this Gantt chart is formed by this? What is the Gantt chart? Basically, Gantt chart is formed to show the arrival time and waiting time of these processes. So if we draw this Gantt chart as this P1 is arrived at time 0, because it is the first process now. So at time 0, P1 arrives. So we put it here 0, and then this is the P1, and it takes how much CPU burst time? It takes 24 milliseconds. So as this CPU scheduling is non-preemptive, so no other process can preempt it. So therefore it is executed till 24 milliseconds. Until and unless that P1 process finished, that P2 process cannot come. And after 24, that P2 process will come, that P2 process, and what is its time? That is 3 milliseconds. So 24 plus 3 is what? 24 plus 3 is 27 milliseconds. And after that P3 process is arrived. So again, it arrived at 27 milliseconds, and 27 plus 3, it's 30 milliseconds. So this is the Gantt chart. So according to that, now what is the waiting time for P1? As P1 is arrived first now at time 0, so what is the waiting time for P1? P1 waiting time is equals to 0 for obvious. What is the waiting time for P2? As P1 executing for 24 milliseconds, so P2 has to wait at least for 24 milliseconds. So what is the waiting time for P2? That is the 24 milliseconds, and P3 get the CPU on after 27 milliseconds, after P1 is finished and P2 is finished. So that P3 got the CPU at the 27 milliseconds, and what is the waiting time for this P3? That is the 27 milliseconds. So now we can calculate on the basis of that the average waiting time. So average waiting time for these this FCFS order, if we assume that FCFS order is following. So the average waiting time is 0 plus 24 plus 27. This is for P1, this is for P2, this is for P3. Divided by 3, because 3 processes are there. So that is the 17 milliseconds is there. We can write here 17 millisecond. That is the average waiting time. Okay. Now let's assume this is the waiting time for in this situation. So now we assume that if there are 3 processes are there, P1, P2, P3, and suppose the processes arrived in the order of P2, then P3, then P1. This is the, table here, and we are assuming that these processes arrived at, first is P2, bus time is 3, second is P3, bus time is 3, and P1, that is bus time is 24. Same is there, bus time is same. There is no change of bus time, but order is different, P2, P3, P1. So when P2 comes, so again, because it comes first, so waiting time for, P2 is 0, so at time P2, 0, time, T0, it's arrived P2. How much bus time of P2? This is the 3 millisecond. So that executed till, 3 millisecond, and after, 3 millisecond, next, process comes, that is the process P2, P3, and this is the, processing time for P2. At P3, this arrives and it executed again 3 for 6 millisecond. That means 3 plus 3, 6. And at 6, that P1 arrived, and what is the what is the bus time for this? That is 24. So 6 plus 24 becomes 30. So in this situation, what is the waiting time for P1? That is, the waiting time for P1 is 6, because it has to wait for 6 milliseconds. P2, waiting time for P2 is 0, because it arrives first in the order of, FCFS order. And what is the waiting time for P3? That is the 3 millisecond, because it has to wait until unless P2 has finished its work. And at that moment that we calculate the waiting time, we can calculate the average waiting time as well. So average waiting time in this situation, 6 plus 0 plus 3 and divided by, 3, because 3 processes are there. So that is the 3 millisecond, waiting time in this situation. So this reduction, is substantial. You can see that here is waiting time is 17 millisecond, and drastically, reduce that waiting time like 3 millisecond. So thus the average waiting time under, FCFS policy is not minimal, and, may vary differently if the process, CPU bus time vary greatly. So in addition, you can say, consider the performance of FCFS scheduling in a dynamic situation as well. Assume, we have one CPU bound process and many IO bound processes are there. And as the processes, flow around the system. So at this situation, what will happen? The CPU bound process will get the CPU and hold it during this time, and all other processes will finish their, IO and move into the ready queue and waiting for the CPU. So while the processes wait in the ready queue, so in that situation, the IO devices are idle because they have no work. So eventually the CPU bound process finishes its CPU burst and then, moves to the execution quickly and move back to the IO queue. So at this point of time, the CPU sits, idle, and the CPU bound processes will then, move back to the ready queue and allocate that, particular, process and to the CPU. Again, all the IO processes end up waiting in the, ready queue until the CPU bound process is done. So this process is going on. So that effect is known as a, convoy effect. As all, the other processes which are waiting for the one big process to get off the CPU, that effect is known as a convoy effect, in which short processes are, waiting for the longer time. It is just the situation like that. For only 3 millisecond, they need that P1 and that P2 and P3 need only 3 milliseconds and 3 milliseconds time for the CPU burst. But they have to wait for P2 wait for 20 milliseconds and that P3 wait for 27 milliseconds. That effect basically is known as a convoy effect, when short processes behind long processes. They wait for the longer process. So that, FCFS scheduling is non-preemptive. So once the process has been allocated to a process, that process keeps the CPU until and unless it releases the CPU, either by, terminating the process or by requesting the IO. So that FCFS algo is, particularly, you can say, troublesome for time sharing system as well, where each user need to get a share of the CPU at regular interval of time. We will discuss later on what is this time sharing system, although we have some idea about time sharing, operating system in our previous classes when we discuss about the introduction of operating system. So this is all about, FCFS policy, that scheduling algo which perform on the basis of first come, first serve scheduling. So I hope this is clear to you all, that FCFS scheduling, and these are some reference books are there, and you can refer these for your further readings as well. So thank you for watching this video. Thank you all of you.